Okay, thank you. So this is an update and maybe introduction to Girder. Girder is a data management system for the web written in Python, and it's newer to the ecosystem here. There's a very nice talk yesterday by Casper, Matt Turk, a project where he used Girder and Fuse to create a reproducibility system. Very impressive. Take a look at that. So Girder is data management, but there's oodles of data management systems out there. And why do we care here about this one? It's because it's focused on science, meaning reproducibility and organization and discovery of data. Those are the goals of the project. And exactly what do we mean by data management? It means storage, access, sharing of files and metadata, and browsing, viewing, and sharing data behind a single abstraction. So one nice abstracted place, and what Girder takes care of is this storage and access and metadata. Why was this made this way? So it's architected in a way that it is flexible and extensible, really designed as part of it, and it allows you to integrate visualization and analytics into what you do with the data. So things like VTK, ITK, or anything in the scientific Python ecosystem, we can run on the data. And exactly what does Girder provide in terms of the value that it adds? Data indexing, browsing, searching, filtering through data. Provenance, so you can know what happens to data as it is transformed through operations. Abstraction, exposing data in a more uniform way, no matter where it is. So you have many data storage backends, and it's exposed in this uniform way. And it can be applied across many different scientific domains: medical imaging, histopathology, geospatial domains, chemistry, computer vision, neuroscience, other domains. It applies equally in all these domains. And some of the things you can do, for example, is managing all this data, but then build plugins. One of the popular plugins is the Girder worker, and this can allow you to take a Python script or a Docker image that has some execution and do batch processing on all your data, and it will run it through all the data. You can keep track of the execution for some long-running operations on the data. So the near-term roadmap is deeper integration with Jupyter Lab. There's now an extension that is along the way, but also improved metadata querying, feed analytics, cohort construction, better provenance, and much further ahead is, or not too much further ahead, is in the big picture enabling infrastructure for software-centered science, doing algorithm development, and also interactive browsing of complex scientific data sets. Here's more information. Here's the link.
Thank you. All right. Up next, too many things in my hands, we have PyMC3, and on deck is GeoPandas.
Good afternoon, everybody. I'm happy to be here to give a quick update on PyMC3. For those of you who don't really know what PyMC3 is an awesome probabilistic programming language written in Python. So a probabilistic programming language is used for Bayesian statistical modeling. We did a tutorial here at SciPy 2018. And a PP language, a probabilistic programming language, provides a library of probability distributions, sampling algorithms, and syntax to glue it together. And there's been a lot of use in it in a wide variety of fields: marketing, finance, astrophysics, biomed. Where you need to do statistical modeling, PyMC3 can come in handy. In addition to providing all of that, there's a bunch of tooling for visual tools for your Bayesian workflow, right? This is becoming a thing in the field. And so we provide, there's a bunch of plots that are being developed, that have been developed and put inside PyMC3, and so this helps you do things like model diagnostics and the likes, and visual inference as well. Now, in addition to that, PyMC3 does have a wealth of learning resources that are available online. So for example, there are videos, there are tutorials, there are talks, there are books, ebooks freely available that are online as well. So if you're interested in Bayesian statistical inference, PyMC3 is a great tool to learn. That said, PyMC3, for those of you who are using PyMC3, you will know that it's written on top of Theano. and recently Theano has been announced that the Theano team has announced that they're not further developing Theano anymore. So what then will happen to PyMC3? Well, that's what I'm here to tell everybody about. Since Theano is not being developed any further, the PyMC3 core dev team will take over Theano until PyMC4 is released. And it's explicit that we are explicitly not releasing or accepting any new features into there. Then what about PyMC4? Will it still retain the same good API that PyMC3 has provided? And the answer is yes, plus some new experimental model building APIs that will let you chain models and compose models together, so it's gonna look pretty exciting. All right, so that's it for me. If you're interested in learning more, these are the URLs, take them down. Thank you very much.
All right, up next is GeoPandas, and on deck is Dask.
Okay, so I'm Joris. I'm going to show you GeoPandas, which I put a nice tagline, easy, fast, and scalable geospatial analysis in Python, which is somewhat true. What is GeoPandas? It extends the Pandas data frame with support for geospatial data, but with focus on vector data. So if you have point, line, strings, polygons, think shapefiles, and it combines many existing libraries under the hood. It's very similar as to how PostGIS extends PostgreSQL. So you have a data frame with a geometry column, and then many of the geospatial methods are available on this object. There is an upcoming release that I hope to be able to release somewhere during the sprints of after, with a much improved overlay function and some other very nice functionality. So the current GeoPandas, or the next release, makes it easy to work with geospatial data. Is it also fast? Depending on the size of your data, it's not that fast, but there is an in-development version currently based on Cython to speed up, to provide very nice speed-ups. Yeah, I'm not going into the details here, but hopefully in the future we can have a version of GeoPandas that can be much faster than the current one. So it needs some attention, some time to get that finished, but it's already certainly functional. There is a branch that you can check out if you're interested. Is it also scalable? That's much more experimental than the slide before. There is a prototype of building a Dask collection for GeoPandas based on geodata frames, and we have a working benchmark, a prototype of a parallel spatial join. So it's certainly showing that something is possible, and if you're interested in that functionality, yeah, feel free to contact me or Matt to get involved to take this forward.
Up next is Matt Rockland with Dask, and on deck is Xray.
So hi everyone, talk about Dask. So the mature parts of Dask became marginally better. So things like Dask Array, Dask Data Frame, Dask Delayed, Xray up next. Also the schedulers haven't changed in any substantial way over the last year, except generally getting better. If you like things that work, you should use these things. There was a nice tutorial given this year by Jim Chris, Martin Durant, and Tom Augsburger. So if you're interested in these things, go there. Some immature components matured, some didn't. There's been some very active work on machine learning recently. Olivier Grisel gave a talk earlier today, I believe, on scikit-learn and Dask and how they can work better together. There's other parts didn't mature. So GeoPandas was, I think, done sometime a while ago. Also Dask Image. There's a lot of good work in image processing, but it's only been in Dask Array. These are some good opportunities people want to get engaged in Dask. One can use Dask in many different domains, and it's actually quite pleasant to go into GitHub, search for Dask in recent issues, and see all of the projects start to adopt it. So there's many different opportunities. Please come chat if you want to start building things. Dask is sort of matured to a point where the core is good, and now it seems to be spreading out horizontally. That's a good opportunity to become engaged in the project. A large change in the last year has been focused on deployment. So The three sort of major places in which Dask is being deployed today are on traditional supercomputers, on Kubernetes, on the cloud, and then very recently on Hadoop clusters with Dask Yarn. These are all we've sort of solidified around a standard interface, a standard user experience. It seems to be working fairly well. This is a major change of the last year. I want to end with a case study. So this is the Pangeo community. This came out of Xray developers and Dask developers and a lot of Earth and atmospheric scientists. And we got together, we wrote a grant, we were funded together. We're doing, I think, some very good science and some very good software development together. It'd be very nice to replicate this process with other scientific domains. I think we do the same thing for many other groups. It's been a very nice sort of software sustainability model that I've really enjoyed. Getting a grant with both scientists and software engineers in the same group. So, and if you're interested in that, there was a Pangeo talk by Joe Hammond, I think on Wednesday. That's it. Thank you.
So up next we have Stephen Hoyer with Xray, and on deck is Phil Ellison with Caterpie.
Great. So I'm going to tell you a little bit about what's been going on with the Xray project. So first, what is Xray? So Xray is a project for multidimensional labeled arrays and datasets in Python. And usually people think about it in a couple of different ways. One is if you use NumPy, it adds axis names and axis labels on top of NumPy. If you're familiar with pandas, you might think of it as a multidimensional generalization of a pandas data frame. Or alternatively, if you know what a netcdf file is in the geosciences, it's an in-memory netcdf file. So with Xray, you can do all the operations you'd like to do, say, with NumPy, except with names instead. So using the names of your axes, the names of the coordinates you're pulling out, and it's a pretty complete ecosystem for doing those sort of operations. And it's a domain-agnostic project as well. A couple of things that are sort of relatively new in Xray that I'd highlight. One is we wrote a new tool for making it easier to extend Xray, to add sort of a labeled wrapper on top of your function that works on NumPy arrays. That's this apply ufunc. And it's something that is, it also lets you parallelize things with Dask. It built on top of this abstraction from NumPy called universal functions that are really powerful in general, and I encourage you to learn more about. Even they'll kind of blow your mind when you finally figure it out. Okay, something else that's new that I'm very proud of, done by another Xray developer, is we finally have like a fully general multidimensional version of vectorized indexing and interpolation. So this is like NumPy's vectorized indexing, except it's sort of referencing things with the names of the dimensions that you're indexing with determine the dimensions of the result. So you can use this to do very powerful sort of arbitrary reshaping and interpolation of data, like sort of a reprojection and regridding operation. This does interpolation as well as just normal indexing. What's next? Yeah, is that we're trying to build new interfaces for making it easier to extend Xray, like different file formats, different custom indexing schemes or grid schemes, and especially arrays, different types of array systems. And this is how we plan. How we plan to. Especially we're doing this work inside NumPy. So for things like sparse arrays, arrays of physical units, distributed arrays, we want to make a generic system for doing that and plugging that. And so we're doing that work in NumPy down upstream, so that hopefully we can use it in Xray and other people can also benefit. And that's it. Yeah.
All right, so next we're going to hear about Caterpie and Iris. They're on the same slide deck, right?
Yep.
Okay, good. And up next is Pei Lian Lin to tell us about Astropie.
Okay, hi. So this is a bit of a duo to talk about some of the CITLS projects. So I'll start with Caterpie. Caterpie was originally developed to kind of visualize gridded data products for research and operational purposes. It's got this kind of generalized object-oriented map projection definition setup. And it's super easy to kind of extend that. And the benefit you get, image, geometry, vector field transformations in kind of a general abstract form. It's got this optional interface that gives a really powerful, intuitive matplotlib kind of mapping API. Yeah. I guess the other thing I wanted to add on that, so as well as matplotlib, there's a bunch of other tools that have kind of started to adopt Caterpie. So GeoViews we've been seeing a bit of, and other tools such as SciPy started to kind of pick up on the Caterpie map projection setup. Despite that kind of broad appeal within SciPy, we're still fairly limited in terms of the core developer group. So I just wanted to show our numbers. That's definitely a priority for Caterpie, is to kind of grow that core maintainer kind of sustainability angle. One of the implications of that fairly small group is that we do have a fairly slow release cadence, about once a year at this point. But despite that, interfaces are starting to mature quite nicely. We're definitely tracking kind of things like upgrades to Matplotlib and Proj 4. But there's definitely loads of room for improvement still. We're aware of quite a number of those kind of bigger things that we'd like to work on. For instance, being able to convert between those object-oriented Caterpie projection definitions in Proj 4. And that would really unlock some powerful interoperability between things like Fiona, Rasterio, GeoPandas, and some of the other geospatial stack. Direction of travel is really good. As I say, Caterpie needs to prioritize on kind of building that core maintainer group. We're going to be sprinting on Caterpie this weekend, so if you're interested in geospatial visualization, come and check us out. There's loads of things that we can improve. And since Basemap's announcement earlier last year, for deprecation, they announced Caterpie as the suggested alternative or replacement. They've definitely noticed an uptake, a spike in uptake, and questions on Stack Overflow. So kind of, again, healthy direction of travel.
Okay, so I'm going to quickly talk about Iris. Going to zip through this pretty quick. So you heard from Stefan earlier on. Iris and Xray are pretty much in the same sort of space, handling n-dimensional data. What's the difference? Small, but a big thing for us is that we think Iris understands the data because it understands the metadata. Why is that? Because we're based on the CF metadata convention. So you think it's not more than a NumPy array, it's actually wrapping your metadata around that. So if you know the convention, you know about, it knows about the data coordinate systems, your SI units, your standard names, all that kind of stuff. So if you know that, you get that with Iris, and it makes life easier, really. And because they have the format agnostic format, we can ingest different formats like NetCDF, like GRIB, PP, and any other sort of custom format that you want. Moving on, same as Caterpie. Iris is core to the Met Office. We've got a growing maintainer base, and people are building on it, which is good. We've been working hard to curate things and squash issues and feature requests, try to do as many of those as we can. Speaking of feature requests, yeah, what we're going to be heading on next is we're going to be looking at CF 1.7, the latest convention there. Also, getting quite excited, we're going to look at 2D U-grid support and cube sphere meshes. Said those words in the right order. We're looking to that to help the Met Office in a new model. With DAS, that's been awesome. They've helped about loads, and we're working with Pangeo, so optimizations are coming in through there. Summary, we've cut version 2 with Dask replacing Biggest. That was awesome, thanks to the Dask guys. They made that happen with masking. And, oh yeah, with we're also curating our software stack, the Caterpie, Condo Forge, things like that, and CF Units. CF Units super fast. That's just, it's there. You can use it, pulled out of Iris because it stands on its own. People are using it. We Cythonize it to make it quicker and understand more calendars, and it uses CF. Save time now, doesn't it? Yeah. Whew, that's me. Thanks.
Right, so up next we have Haley and Lynn telling us about Astropie, and on deck is Scott Christensen to tell us about Quest.
Hi, can you hear me? Yeah, okay, all right. So I'm here to talk about Astropie. When you hear Astropie, I think most of you would think about the package. So, sorry. Most of you would think about the package, but Astropie is actually has grown into an ecosystem. We call it the Astropie project, and the package is the core library of it. If you want to learn more, here's the URL is astropie.org. We also have affiliated packages. These are packages that are either going to be merged into the core library in the future when they stabilize, or they are specialized and but they are very integral to the ecosystem, so we call those affiliated packages. And we also do a lot of community support. We have a whole repository focused on tutorials, how to use Astropie and affiliated packages to do science in astronomy. And we participate in Google Summer of Code under Open Astronomy umbrella. In fact, I think we have a few students doing that program right now for this summer. We, of course, also have to support our own infrastructure. We have helper packages, package template, not very unlike the cookie cutter presentation you saw a few days ago. We have continuous integration. APE is Astropie proposal for enhancements. It's kind of like PEP, but for Astropie. Benchmarks, and a bot that we love. Once in a while, we also publish science papers. We published one in 2013 and just published a follow-up paper this year. And coming soon in coordinated packages, if you want to know more about it, you can read 8.15. So due to time constraint, I won't talk too much about that. So here are the affiliated packages. Don't have time to talk about them either, but you can go to the URL to learn more about them. They cover a lot of fields in astronomy. Very nice, very useful. And this is not a final list. There are active applications into Astropie project to be affiliated, and they'll be reviewed and added in the future. So just a quick update on the core library itself. It's running on a 6-month release cycle, but we do bug fix in between as needed. So version 2 is kind of a long-term support, and we only do bug fixes, and only until 2019 is the last version that supports Python 2. Version 3, we drop Python 2 support, and these 2 versions on the screen are just released June 1st, update your Astropie. And 3.1 will be the performance release. Thank you.
Thank you. Sorry to cut you off. All right, up next we have Scott Christensen to tell us about Quest, and on deck is Oliver Zeigerman to tell us about Altair.
Hi, I'm Scott Christensen. I work for the Army Corps of Engineers. I'll talk about a library that we've created to help with some of our data management at the Research Center for the Army Corps called ERDIC. The main challenges that we're trying to address here are data discovery and what I like to call the second death of data. That's when the guy that wrote the model and had it saved on his computer left and he no longer remembers where it is, or it's now gone forever. So we want to be able to capture some of that data so that it's rediscoverable. So I'll briefly mention kind of a set of tools that we use in coordination, but may go more into detail on Quest itself, which is our Python API for accessing data. There's also a web interface for Quest that's written in Tethys, which is a Django-based web framework for GIS applications. And then we also have a data repository that's based off of HydroShare. Again, a Django-based metadata server, and it uses iRods underlying for data management. So kind of our approach here, we've got a lot of different data sources, and rather than waiting for a standard API or a standard format for all of these disparate data sources, we created an API and then write plugins to connect to all the data sources out there that we're interested in, or are working on creating those plugins. And so Quest itself is this extensible framework. There are 3 different types of plugins. We call data sources, like I just showed, we call those providers. So there are provider plugins that describe how to connect directly to different data sources and download that data. Filters are just ways of transforming data. And then I/O, just getting data on and off of disk. So it's very extensible. Where we're going is that we'd like to, rather than having all of these plugins within Quest itself, we would like to use external libraries like Intake, the Anaconda is just released to handle I/O. Ulmo, we'd like to push a lot of the data providers back into Ulmo, which is an existing Python library. And then we're looking for something for filters, but we're adding more filters. So here are the repositories. Thank you.
This change is a little more complicated because I ran out of desktops.
Can you zoom in a little bit? Okay, perfect. One more. Yeah.
All right. Okay. And on deck is Tim Hopper.
Okay, I'm going to make this fast. So this is about Altair, and Altair is a visualization library. And for me, well, I'm not an expert at it. I just used it, and it's perfect for me to quickly explore data sets. It's for exploration, more or less, not to show these visualizations to other people. Maybe it's also suitable, but for me, it's great for exploration. So it's based on the idea of grammar of graphics. That means if you have an idea what that might be, it's pretty easy to, it's pretty approachable. And what I did, I just loaded my data. Hopefully it's big enough now. Maybe I zoom in more. One more? Good? Okay. So I loaded in my data, and it's the data that I used for my poster. So I actually used this stuff. It's a pandas data frame, and it contains some columns. Doesn't matter too much which they are. And then with this single line, you can come up with this plot. So what you're doing is you pass in the data, you tell it the mark, which is part of the grammar of graphics, is a point, and then you encode the data to the visualization. And that's pretty good. I mean, that's just one line, and then you see things, but maybe not too much, and then you do a little bit more, but only a little bit. You specify the colors, and then you have something that's interactive. I'm not quite sure how to make it interactive on this touchpad here, but it would be, trust me. And then if you want to go really fancy, with little, I mean, how many lines is this? 10, maybe 20? You get something like a cross-filtering thing, where all the dimensions plotted here, and I hope this works. No, it does not. That's pretty unfortunate, but it would be extremely impressive if it worked in this, because I could actually do something like cross-filtering. I would select here, and then if I select it here, it will also select here, and I could like combine a lot of filters on these different dimensions. And this is just a few lines of code. I tweeted the link to the notebook, so if you actually execute this, it will work. So, okay, I'm done. Thank you.